seismic monitoring networks across the Cascade Range detect a pattern that sends ripples of concern through the scientific community. These are not the dramatic earthquakes that typically herald volcanic activity. Instead, the data show the steady, relentless expansion of magma chambers beneath peaks that have slumbered for centuries. Scientists find themselves witnesses to a geological awakening that could reshape the Pacific Northwest. Dr. Michael Torres examines real-time data streams from dozens of monitoring stations, each one confirming the same unsettling trend. Volcanic systems from Mount Baker to Mount Shasta show synchronized inflation signatures. The coordinated nature of this activity suggests forces at work on a scale that transcend individual volcanoes. Something is stirring beneath the entire Cascade arc, and the scientific community is racing to understand what it means. At 6:42 a.m. Pacific Standard Time, GPS station MABA on Mount Baker's northwestern flank recorded a vertical displacement of 2.3 millimeters since the previous day's measurement. For most monitoring networks, such movement would fall within the margin of error, but Mount Baker's baseline had remained stable for over 18 months. The sudden shift triggered automated alerts across the Cascades Volcano Observatory monitoring system. Seismometer arrays positioned throughout the North Cascades detected a subtle but persistent tremor signature beginning at 4:15 a.m. Unlike the sharp jolts of tectonic earthquakes, these signals showed the prolonged low-frequency characteristics associated with fluid movement deep underground. Station SHUK, located 12 kilometers southeast of Baker's summit, recorded continuous harmonic tremor with dominant frequencies between 1 and 3 Hz. The pattern matched textbook examples of magma migration. Gas monitoring equipment at Sherman Crater, Baker's active thermal area, registered a 15% increase in sulfur dioxide emissions over the past 72 hours. Automated spectrometers detected elevated concentrations of hydrogen sulfide and carbon dioxide, chemical signatures that often precede periods of increased volcanic unrest. The gas ratios suggested deeper source material reaching the surface, a shift from the typical shallow hydrothermal emissions that characterize Baker's normal background activity. Thermal infrared cameras positioned on nearby ridgelines captured temperature anomalies across the crater's fumarole fields. Surface temperatures that typically ranged between 45 and 60 degrees Celsius now peaked at 78 degrees Celsius in several locations. The thermal signatures appeared most pronounced along the crater's eastern rim, where new steam vents had opened sometime during the previous week. Dr. Jennifer Walsh, a research geophysicist with the USGS, arrived at the Cascades Volcano Observatory before dawn to review the converging data streams. The overnight reports painted a picture of a volcanic system transitioning from dormancy to unrest. Each monitoring network told the same story from different perspectives. The ground was moving, the deep plumbing was active, and the chemistry was changing. INSAR satellite data from the European Space Agency Sentinel-1 constellation provided the broader context. Radar interferometry measurements spanning the past 6 months revealed a subtle but measurable inflation pattern centered beneath Baker's summit. The deformation extended in an elliptical pattern roughly 8 kilometers long and 5 kilometers wide, with maximum uplift rates approaching 1.2 centimeters per month. Similar patterns were emerging across the Cascade Range. Mount Rainier's monitoring network detected comparable ground deformation beginning 3 weeks earlier. GPS stations around Mount St. Helens recorded accelerating uplift rates that had doubled since early November. Even Mount Hood, typically one of the quieter Cascade volcanoes, showed signs of subtle inflation in its southeastern quadrant. The synchronization troubled scientists more than any individual measurement. In the basement laboratory of the Cascades Volcano Observatory, Dr. Michael Chen processes INSAR satellite data that reveals the true scope of what is happening beneath the Cascade Range. The European Space Agency Sentinel-1 radar measurements, collected every 12 days, create a time-lapse movie of ground deformation spanning the past 18 months. What emerges from the analysis defies conventional understanding of volcanic behavior. The interferometry maps show Mount Baker's magma chamber expanding at a rate of 0.8 cubic kilometers per year. For comparison, the chamber's total estimated volume before this inflation episode was approximately 15 cubic kilometers. The current expansion rate means the chamber is growing by more than 5% annually, a pace that volcanic models suggest cannot be sustained without triggering significant eruption activity. Depth calculations place the inflating chamber between 6 and 9 kilometers beneath Baker's summit. At these depths, magma exists under enormous pressure, contained by the overlying rock column that acts like a geological pressure cooker. The chamber walls, composed of crystalline basement rock and older volcanic deposits, can only stretch so far before reaching their elastic limit. Computer models running on the observatory's high-performance systems calculate the stress accumulation within the chamber walls. Current pressure estimates range from 200 to 350 megapascals, approaching the threshold where rock failure becomes inevitable. The models incorporate chamber geometry, magma viscosity, and wall rock strength to predict when the system might reach critical pressure. Dr. Sarah Martinez, a geophysicist specializing in volcanic deformation, explains the mechanics driving such rapid inflation. Fresh magma injection from deeper sources provides the most likely explanation. Basaltic magma rising from the mantle encounters the existing chamber, adding both volume and thermal energy to the system. The temperature differential between incoming basalt at 1,200 degrees Celsius and resident magma at 900 degrees Celsius creates convection patterns that further pressurize the chamber. Gas saturation analysis reveals another critical factor. As magma pressure increases, dissolved gases such as water vapor, carbon dioxide, and sulfur dioxide begin to come out of solution, forming bubbles that dramatically increase the magma's volume. This process, similar to opening a pressurized soda bottle, can accelerate chamber expansion exponentially once it begins. The inflation pattern extends beyond Mount Baker. Satellite data confirms that Mount Rainier's chamber has expanded by 0.3 cubic kilometers over the same period. Mount St. Helens shows more modest but measurable inflation of 0.1 cubic kilometers. Even Mount Hood displays subtle deformation signatures consistent with deep magma intrusion. Regional analysis suggests a coordinated magmatic event affecting multiple volcanic systems simultaneously. The pattern implies that deep crustal processes are driving magma production and migration on an unprecedented scale. At 7:30 a.m. on November 15th, an emergency meeting convenes in the conference room of the Cascades Volcano Observatory. Dr. Seth Moran, the observatory's scientist in charge, addresses a room filled with volcanologists, seismologists, and emergency management officials. The overnight data has crossed critical thresholds that trigger enhanced monitoring protocols established after the eruption of Mount St. Helens in 1980. The USGS Volcano Hazards Program activates its rapid response team within hours of the meeting. Additional seismometers arrive by helicopter at strategic locations around Mount Baker's flanks. GPS stations with real-time telemetry capabilities are installed at sites that previously relied on periodic manual surveys. The enhanced network will provide minute-by-minute updates on ground deformation and seismic activity. Dr. Carolyn Dridger, a volcanologist with 3 decades of Cascade Range experience, reviews the inflation data with growing concern. She recalls the precursory activity before the awakening of Mount St. Helens in 1980, when ground deformation preceded the catastrophic eruption by several weeks. The current Baker inflation rates exceed those historical measurements by a factor of 3. Field teams deploy across the North Cascades, installing temporary monitoring equipment at locations identified by computer modeling as critical observation points. Each station costs approximately $45,000 and requires helicopter transport to remote alpine locations. The investment reflects the scientific community's assessment that this volcanic unrest represents a genuine threat to regional safety. International collaboration begins immediately. The Alaska Volcano Observatory shares expertise from monitoring similar volcanic systems along the Aleutian Arc. Italian volcanologists from the Osservatorio Vesuviano provide insights from their experience with Campi Flegre's ongoing inflation crisis. Japanese researchers contribute real-time analysis techniques developed for monitoring Mount Fuji's subtle deformation patterns. Dr. Michael Poland, a research geophysicist specializing in volcanic deformation, explains the significance of the current measurements to assembled emergency managers. Magma chamber inflation at the observed rates typically precedes eruption activity within months to years, not decades. The timeline uncertainty creates challenges for emergency planning, but the trend direction is unmistakable. Enhanced gas monitoring reveals chemical signatures that support the magma intrusion hypothesis. Helium isotope ratios measured at Mount Baker fumaroles show increasing contributions from mantle sources, indicating fresh magma injection from depth. Carbon dioxide flux measurements have tripled since monitoring began in earnest 3 weeks ago. Communication protocols established after previous volcanic crises ensure that information flows rapidly between scientific institutions and emergency responders. The National Weather Service receives real-time updates for aviation safety advisories. The Washington State Emergency Management Division coordinates with county officials in communities near Mount Baker. Expert assessment meetings occur twice daily, with participants joining by video conference from monitoring stations, universities, and government agencies across the Pacific Northwest. Historical volcanic databases reveal patterns that place the current Cascade inflation in a sobering context. The 1980 eruption of Mount St. Helens began with ground deformation rates of 1.5 meters per day in the weeks preceding the catastrophic blast. The bulge on the volcano's north flank grew by 2 meters vertically and 1.5 meters horizontally before the slope collapsed in the largest landslide in recorded history. The current Baker inflation, while more gradual, follows a similar trajectory when adjusted for chamber depth and magma composition. Computer analysis of the 1980 precursory data shows that St. Helens's chamber expanded by approximately 0.1 cubic kilometers in the final month before eruption. Baker's chamber has grown by 0.8 cubic kilometers over 18 months, suggesting a much larger magma intrusion driving the current unrest. Yellowstone's inflation episodes provide another troubling comparison. From 1996 to 2003, the Yellowstone caldera floor rose by 17 centimeters as magma intruded at depths of 6 to 10 kilometers. The inflation paused for several years before resuming in 2014, with uplift rates reaching 5.5 centimeters annually. Scientists monitoring Yellowstone noted that such sustained inflation creates conditions for potential catastrophic eruption. International case studies reveal the global significance of rapid chamber inflation. Italy's Campi Flegrei caldera has experienced episodic inflation since 1950, with the most dramatic episode occurring between 1982 and 1984, when the ground rose by 1.8 meters. The inflation triggered thousands of earthquakes and forced the evacuation of 40,000 residents from Pozzuoli. Despite decades of continued unrest, Campi Flegrei has not erupted, demonstrating that inflation can persist for years without culminating in volcanic activity. Alaska's Mount Cleveland provides a more recent example of inflation leading to eruption. Satellite monitoring detected chamber expansion beginning in 2009, followed by explosive eruptions in 2011 that sent ash plumes to altitudes exceeding 10 kilometers. The Cleveland sequence showed that even modest inflation can produce significant eruptions with regional impact. Statistical analysis of global volcanic inflation events reveals disturbing trends. Of 47 documented cases of rapid chamber inflation since 1980, 34 resulted in eruptions within 5 years of initial detection. The eruptions ranged from effusive lava flows to explosive events reaching VEY4 on the Volcanic Explosivity Index. Dr. Charles Mandeville, a volcanologist with the Smithsonian's Global Volcanism Program, emphasizes the unprecedented nature of the current Cascade activity. Multiple volcanic systems showing synchronized inflation has no historical precedent in the modern monitoring era. The pattern suggests regional-scale magmatic processes that could trigger coordinated eruptions across the volcanic arc. The Mount Baker inflation rates now exceed those recorded at any Cascade volcano since instrumental monitoring began. Computer modeling laboratories at the Pacific Northwest Seismic Network run eruption scenarios around the clock, processing thousands of variables to predict potential outcomes from the current volcanic unrest. The simulations incorporate chamber pressure, magma composition, gas content, and structural geology to generate probability maps for different eruption magnitudes. What emerges from the analysis reveals the staggering scope of potential regional catastrophe. A VEI3 eruption, considered the most likely scenario given current inflation rates, would send an ash column 12 to 25 kilometers into the atmosphere. Prevailing westerly winds would carry the ash plume eastward across Washington state and into Idaho and Montana. Computer models show that Seattle would receive 2 to 5 centimeters of ashfall within 24 hours, enough to collapse roofs, clog water treatment facilities, and shut down all air traffic across the Pacific Northwest. The economic modeling proves equally sobering. A moderate eruption would disrupt Interstate 5, the primary transportation corridor connecting Seattle to Vancouver and Portland. The highway carries $3 billion in trade annually, and even temporary closure would cascade through regional supply chains. Agricultural areas in the Skagit and Whatcom valleys, which produce $2.8 billion in crops yearly, would face complete devastation from ashfall and pyroclastic flows. Pyroclastic flow calculations reveal the most immediate threat to human life. These superheated avalanches of gas, ash, and rock can reach temperatures of 800 degrees Celsius and travel at speeds exceeding 100 kilometers per hour. Computer simulations show that pyroclastic flows from a major Baker eruption would follow the Nooksack River Valley, potentially reaching populated areas near Deming and Everson within 30 minutes of eruption onset. Lahar modeling presents an equally terrifying scenario. Volcanic mud flows triggered by rapid snowmelt from Baker's extensive glacial system would surge down river valleys at speeds approaching 60 kilometers per hour. The Nooksack River system could carry lahars directly into Bellingham Bay, while flows down the Baker River would threaten communities along the Skagit River corridor. Exposure analysis reveals that approximately 180,000 people live within the primary hazard zones for a major Baker eruption. The cities of Bellingham, Mount Vernon, and Sedro-Woolley fall within areas that could experience significant ashfall, lahar inundation, or pyroclastic flow impact. Evacuation modeling suggests that moving this population to safety would require 72 to 96 hours under optimal conditions. Infrastructure vulnerability assessments paint a grim picture of regional resilience. The electrical grid serving northwestern Washington relies on transmission lines that cross multiple volcanic hazard zones. Ash accumulation of just 5 centimeters can cause widespread power outages by creating conductive pathways that short-circuit high-voltage equipment. Water treatment facilities lack adequate filtration systems to handle volcanic ash, potentially leaving hundreds of thousands without clean water for weeks. Emergency management meetings convene in county buildings across northwestern Washington as officials grapple with evacuation scenarios that dwarf any previous disaster planning. Whatcom County Emergency Management Director Lisa Parks reviews population density maps that reveal the staggering logistics of moving 180,000 people away from volcanic hazard zones. The county evacuation plans, designed for coastal tsunamis affecting 30,000 residents, prove woefully inadequate for the scale of volcanic threat now emerging. Transportation analysis reveals the first critical bottleneck. Interstate 5, the primary evacuation route, has a maximum capacity of 2,400 vehicles per hour per lane under emergency conditions. Moving the at-risk population would require sustained traffic flow for over 30 hours, assuming perfect conditions and no infrastructure damage. State Route 20, the only alternative east-west corridor, crosses the Skagit River on bridges that volcanic ash could render impassable within hours of eruption onset. Shelter capacity calculations expose another devastating gap in preparedness. The American Red Cross maintains emergency shelters with a combined capacity of 12,000 people across the region. Housing the remaining 168,000 evacuees would require commandeering schools, community centers, and sports facilities across 3 states. The logistics of feeding, housing, and providing medical care for such numbers exceed the resources of any single state emergency management system. Communication infrastructure presents equally daunting challenges. Cell phone towers throughout the hazard zones lack backup power systems capable of operating for more than 8 hours during widespread electrical outages. Emergency alert systems rely on radio and television broadcasts that volcanic ash could disrupt by interfering with transmission equipment. The county's emergency notification database contains contact information for only 40% of residents in the highest risk areas. Medical evacuation planning reveals life and death timing constraints. Hospitals within the hazard zones house approximately 800 patients who cannot be moved quickly. Peace Health St. Joseph Medical Center in Bellingham would need 6 hours minimum to evacuate critical care patients, assuming adequate ambulance resources and clear transportation routes. Nursing homes and assisted living facilities throughout the region house another 2,400 residents, requiring specialized evacuation assistance. Economic disruption modeling shows that even a precautionary evacuation would cost the regional economy over $2 billion. The Port of Bellingham handles $8 million in cargo daily, and closure would ripple through supply chains serving the entire Pacific Northwest. Agricultural operations in the fertile river valleys employ 15,000 seasonal workers whose displacement would affect food production across multiple states. Historical precedent offers sobering lessons about evacuation effectiveness. The 1980 Mount St. Helens evacuation successfully moved 2,000 people from the immediate blast zone, but current population densities around Mount Baker are 90 times higher. The planning sessions conclude with an uncomfortable acknowledgement that current evacuation capabilities could handle perhaps 20% of the at-risk population effectively. The USGS Cascades Volcano Observatory maintains an advisory alert level for Mount Baker, the second lowest designation on the 4-tier volcanic alert system. Dr. Seth Moran addresses the media during the weekly briefing, emphasizing that while the volcanic unrest is unprecedented in the modern monitoring era, there is no immediate indication of an impending eruption. The enhanced monitoring network continues to track chamber inflation, but eruption prediction remains beyond current scientific capabilities. Real-time data streams flow continuously from 47 monitoring stations now surrounding Mount Baker. Seismometers record every micro-earthquake. GPS receivers measure ground deformation to millimeter precision, and gas sensors analyze chemical emissions around the clock. The data feed into automated analysis systems that alert scientists to any significant changes within minutes of detection. Dr. Carolyn Driedger explains the scientific uncertainty that complicates public communication about volcanic hazards. Magma chamber inflation can continue for months or years without leading to an eruption, as demonstrated by ongoing unrest at Yellowstone and Italy's Campi Flegrei. Conversely, some volcanic systems transition from inflation to eruption within weeks, leaving little time for detailed preparation. International scientific collaboration provides additional expertise on the unfolding crisis. The Smithsonian Global Volcanism Program shares comparative data from similar inflation episodes worldwide. Italian researchers from the Osservatorio Vesuviano contribute insights from decades of monitoring Campi Flegre's ongoing unrest. Japanese volcanologists offer real-time analysis techniques developed for complex volcanic systems. Communication protocols ensure information flows rapidly between scientific institutions and emergency management agencies. The National Weather Service receives hourly updates for aviation safety advisories, as volcanic ash poses severe risks to aircraft engines. Public information campaigns attempt to balance scientific uncertainty with the need for community preparedness. The scientific response reflects lessons learned from past volcanic crises, where inadequate monitoring led to tragic consequences. The 1985 Nevado del Ruiz eruption in Colombia killed 23,000 people, partly due to insufficient hazard assessment. The current Cascade monitoring effort aims to prevent such disasters through comprehensive surveillance and clear public communication, though the unprecedented nature of the inflation episode means established patterns may not apply. Across the globe, volcanic monitoring networks face similar challenges in predicting eruption timing from chamber inflation data. The Volcano Disaster Assistance Program maintains rapid response teams that deploy to volcanic crises worldwide. Their experience with over 50 international volcanic emergencies since 1986 reveals a consistent pattern. Inflation episodes create extended periods of uncertainty that test both scientific understanding and community resilience. Iceland's volcanic monitoring system provides a model for managing persistent volcanic unrest. The Icelandic Met Office operates 70 seismic stations and 60 GPS receivers across the island's active volcanic zones. Their experience with the 2014 Bardarbunga eruption, which followed months of inflation and seismic unrest, demonstrates that comprehensive monitoring can provide adequate warning while acknowledging the fundamental unpredictability of volcanic systems. Japan's approach emphasizes preparedness over eruption prediction. Following the 2014 Mount Ontake eruption that killed 63 hikers despite ongoing monitoring, Japanese authorities shifted focus toward rapid evacuation systems and public education. Even the most sophisticated monitoring networks cannot eliminate volcanic risk. They can only provide tools for managing it. Technological advances continue to improve volcanic monitoring capabilities, but fundamental limitations remain. Satellite radar interferometry can detect ground deformation with millimeter precision, but it cannot predict when inflation will trigger eruption. Seismic networks can locate magma movement in real time, but they cannot determine whether rising magma will reach the surface or stall at depth. The Cascade Range volcanic awakening represents a test of modern volcanic hazard management. Enhanced monitoring provides unprecedented detail about ongoing processes, but the ultimate question of eruption timing remains unanswered. Mount Baker's chamber continues to inflate at rates that challenge scientific understanding. In a world of visible disasters and immediate threats, volcanic inflation reminds us that the most significant dangers often build slowly, silently, beyond human timescales. The Cascade Range sleeps restlessly, and science watches, measures, and waits.